Everyone, and welcome back to another video. I know this is not something that you typically see on this channel, but thought I would make it anyways because it was kind of cool, and I hope to make some more like this. And yeah, anyways, as the title says, I want to show off my own custom I2C implementation. Not custom, but basically from scratch. So what you're seeing here, if you know what you're looking at, obviously it's an I2C frame, and so this actually is all done through code that I made myself. The clock, the data sending, and everything else. So all of this was hard-coded as functions. So I have a function that can allow me to send some data by specifying the address and the data that you're trying to send, and it has the acknowledgement bits set in it. So just kind of a quick rundown. As you can see, if I kind of scroll here, you can see that there's the start condition, sorry, in which SDA goes low and then SCL goes low. Yellow's the clock, by the way, and then the blue is the data. So you have the start condition, and then you have, if I look at the middle cursor here with the orange arrow, I consider that, so this is kind of the start here. That's 1 bit, another, it's a second, third, fourth, fifth, sixth, and then seventh, and then eighth. So that's the first byte sent out, and that equates to 2. If I really wanted to, I could change this to show the actual bytes, or sorry, bits. Binary. There we go. Oops, there we go. So as you can see, it is sending. If we remember that I2C samples the data when the clock is high, like this, and data can only change when the clock is low. So we'll see that in a second, but basically, as you can see, we have 0 here, 0, so 0, 0, 0, 0, 0, and then changes to 1, as you can see, when the clock is low. So that's a 1, and that's a 0. And so it is sent out as 8 bits or a byte for the address, because it has the 7-bit address and then the read-write bit. So as you can see, it actually was able to correctly tell that it was a write bit. And by the way, I can actually show this in a second, happening real time. But as you can see, we have 1, 2, 3, 4, 5, 6, 7 address, and then your read-write bit right there, which is 0 for write. And then there's the acknowledge bit right there, and then another 8 bits, sorry, of data. So 1, 2, 3, 4, 5, 6, 7, 8. That's your data right there, as you can see. And if I move this over, we can see that it gives an extra clock pulse and does the stop condition, in which SCL goes high and then SDA. So that's one example that I had. I do have another one, but I can show you guys what happens if I let this run. And so if I restart the microcontroller right here, the ESP32, it's kind of fast. And I can set it to trigger, obviously, but if you really are interested, you can see it real time if I do it like this. So the waveform is going to come in like this. And so then, there you go. Turn off for near. If I reset right here, it's set to automatically send some data, so I can target that now. So I'm going to stop it here, and I'm going to move this right there, and there you go, you see the same signals. And then over here, this was another one that I sent using the same function I made, and as you can see, it is properly sending a test value here that I have. So you have your start 0, 0, 0, 1, 1, 1, 0, 0. This 0 is the read write, and then this is your acknowledgement, and then 0 all across there, and then your stop. And this was actually simulating sending data to this device, this TI sensor, and I was targeting the address 0E, and I was sending this 0000 reset value to that register. So if I actually change this over to hex again, you can see that I was actually writing E to data 0, or sorry, writing to register E the data 0. Obviously it's not acknowledging anything because the device is not set up or even connected on here. But it goes to show that you can literally write an I2C implementation using simple digital writes and reads and some delays. So I'm going to go over the code right now so that you guys can hopefully get an understanding, because all the other videos online I've seen don't really talk about like how to implement this kind of on a really simple level. Okay, so I'm over here on my computer. So I said I was going to mention how I did it in terms of the code, but there's just a lot for me to try and explain, and I'm honestly not the best at explaining this type of stuff. So I decided that I was just gonna put this on GitHub, and I put a lot of comments, as you can probably see. The main thing again is the timing, which is probably the most important thing. But I gave comments for the functions, but I also did leave in my my initial attempt, which also did work, in which I directly wrote the bits. Yeah, but the most important thing that I did want to mention, for those of you who are trying to again understand how all of this works fundamentally on through an hardware abstraction layer, is the timing. I am doing that timing by manually toggling a pin high and low every 3 milliseconds. You could do it like this, or if you really want to, you could use PWM. That makes things a little bit challenging, I think, when it comes down to PWM isn't you have to be more aware of like the frequency, for example. You need to be able to write the, for example, the delays, because that's what I did here. For the timing, I used a bunch of delays to do so. So for example, for every 3 millisecond clock cycle, basically, I have 3 milliseconds to do whatever I need. And the reason why that's so important is because, for example, if you want to set a bit, you can only do that when the clock is low. So you need to know when the clock is low, kind of thing. And doing it manually was pretty easy. And again, all you need to do is just run this clock, or run the clock per se in this section. You don't need to run it anywhere else. PWM, I don't know if there's a way to turn it on and off with Arduino. I haven't worked much with these. But basically the timing was probably the most important thing that I was trying to understand, which is most likely implemented through timers and or with interrupts and stuff like that. And yeah, I I would say again for the timing. If you really want to get a solid understanding of the timing, I would check out this like I guess bit banging example that I have here. Um, so I am trying to send this data, and I did that manually. So I wrote 0, 0, 0 here, and then a 1, and then a 0, a 1, a 0, and then I wrote another 0. Um, and I know that doesn't line up. I'm trying to remember what I was trying to do here. I think I changed the example a little bit. Um, but yeah, so this would be 1, 2, 3, 4, 5, 6, 7, 8 bits. Last one's low. 0, 0, 0, 1, 0, 1, 0, 0. Yeah, I might have to change that before I put it up on GitHub. But yeah, I would say again the timing is really important here. I gave myself 3 milliseconds in between cycles, so um, that means if I wanted to change the data, I would either have to change it. Um, well, you can only change it when it's low, so you only have 3 milliseconds where it's low. In that time in between, you can change the data. So I do that directly here. And then if you're interested in maybe how you would implement that with loops and stuff, then I would definitely check out this section, this send data function. There's a lot going on here, and I put some comments in here, and hopefully it will make more sense. And I did a better job explaining it in the code because I definitely won't explain it well here. But yeah, so if you guys found that interesting, I guess consider subscribing. I do plan on working on making a custom STM32 board because again, I did this so that I could understand how, or maybe a little bit of an idea how, um, you know, those vendors or manufacturers create their hardware abstraction layers for their ARM-based microcontrollers, so like TI and um, ST. I haven't had experience with TI, but from my research and looking it up, they have a lot of hardware abstraction layers, and it just looks way too complicated to understand. So the other thing was I have worked with TI based microcontrollers in the past, like the I2C series, and my experience with them has been more like, again, you have to set up ports, so you directly change port values, um, the registers internally on those port values, and then for example, like timers and interrupts, you need to set those ports and timers up in a specific way. It's just all really confusing. But again, a lot of those companies provide HALs or hardware abstraction layers, which simplify the process. Um, but uh, again, their implementation then requires that you have to follow their rules, whatever they um, set out for it, however they implemented it. So, for example, let's say my send data function, you would have to follow this convention of giving it the device address, the register address, and the data. But say, for example, you wanted to do something else, then, it's kind of difficult. You got to go sifting through all their HALs and libraries to see what you can do, which is, again, pretty difficult and for me, time consuming. But it does give you the benefit of really getting the most out of your system. Because, for example, like Arduino, it's abstracted to a point where it's pretty simple. Um, but with ST and TI, you're going down to the register level directly and changing values, and you're only running what you need, and including whatever libraries that you need as well to get your system running. I don't know, I like going down to that level, but uh, yeah, I do plan on making my own ST based microcontroller, and I have a project that I'm working on that's unnamed at the moment. So um, yeah, if you guys are interested, definitely check it out in the future. Hopefully, I can make some content about that because I did want to talk about the process of that. Um, but for now, I'm still working on it, still having to research a lot of it. But yeah, anyways, again, if you're interested, I will leave this code in the description in the, below to a GitHub. And yeah, if you guys are interested also in those future projects, um, then consider subscribing, I guess. But if you found this boring or whatever, I hope you have a good rest of your day. And yeah, see you guys later.